All right, so this is going to be a fun one. Today we're going to talk about collisions in rotational motion and gyroscopes. So let's first think about work and rotational motion. So we can take an example problem like this. Let's say we have a 1.5 meter long rod with a mass of 20 kilograms that is attached to a pivot point on one end. It's at rest when we apply a constant force of 250 newtons directly to the other side of the rod, so at a length of 1.5 meters away from the pivot point. How much work has been done after one full rotation of the rod? Um, and so there are a few ways we can tackle this, right? Right now, the tools we have to tackle this is if we wanted to, we think about our work, we know is our change in energy, right? And so in this case, if we take our final rotational kinetic energy and subtract out our initial rotational kinetic energy, right, then we can get our work, our amount of work that's done, right? And since it starts at rest, our initial kinetic energy is zero. So we just have to find our kinetic energy, our final kinetic rotational energy. So we could take our one half our moment of inertia times our final angular velocity squared, right? And given we know where the force that's applied, so we have the torque acting on a rod, we have all of our information for our moment of inertia. And so we can find our final angular velocity if we wanted to, and we can get our final kinetic energy. However, that would be a little bit of work. So let's a little bit of work. So let's think about another way to consider the work. So let's forget about using the moment of inertia and finding that angular velocity. We could use the moment of inertia for rod because 1/3 times its mass times its length squared when it's rotated around one of its ends as the axis. But let's just ignore that for a moment and let's instead repurpose our work equation from translational motion. Because if we remember, our work in translational motion equals force times distance, the distance that system is moved, times the cosine of the angle between the force and the distance, right? So why don't you take one moment and think about how we can rework this equation to fit our rotational variables that we're using for rotational motion. And hopefully you arrived at something that looks like this, which is that our analog for force in rotational motion is torque, right? And our analog for change in position, in translational position, or position of our center of mass, is our change in rotation angle, right? And you'll notice that we're missing that cosine theta, and that doesn't apply here because right now, and we will eventually expand this definition in a couple of classes, but right now we're just considering things that are going around in a circle, right? So we've got that rod that we're talking about in this problem. It's spinning around in a circle, and we're going from one position around in a circle to another. And so we know that our torque equals our force times the distance from the pivot point times sine of the angle between those two, which actually, rather than using sine, let's use or rather than using theta, let's use alpha, so it's a different angle. Or of course, we could also call that our force times our perpendicular lever arm, right? So all that's to say that in our torque, we take care of any angle between the force and the distance that force is being applied. And so we don't need that in our rotational equivalent of work here if we're moving through a circle. So this will be sufficient, and we can use that for this problem. Okay, so keeping this new equation for work and rotation in mind, let's gather some information from our problem to solve for this, right? So we know we aren't given the torque in our problem, but we do know our force that we're applying is 250 newtons. We know that it's being applied on one end of the rod, and that rod's distance away from the pivot point. So the length of the rod serves as our R here. And finally, we're trying to figure out how much work is done after one full rotation, right? So our rotation angle, our angular displacement, is one revolution. And we know that for every one revolution, we have 2 pi's worth of radians. And we want to keep everything in radians when we're doing these problems. So our delta theta will be 2 pi. All right, so that means that our work is going to equal our torque times the displacement, the angular displacement. Or if we break down our torque, we got force times radius times our displacement, right? So we plug in some numbers, we get 250 newtons. For our force, we have 1.50 meters as our distance of that force being applied away from the pivot point. And then finally, our rotation angle, we're going through one full revolution. So that is 2 pi's worth of rotation. If we work the numbers there, we should end up with 2,360 joules worth of work. Right. And again, just as a quick note, that also tells us our final kinetic energy, right? Since our work equals our change in energy. And if our initial kinetic energy, so our final kinetic energy minus our initial kinetic energy, and if our initial kinetic energy was 0 because the rod started at rest, then we now have our final kinetic energy that also equals our final kinetic energy. Specifically, rotational kinetic energy. That seems to be all the kinetic energy that this system has. So let's take and look at a collision problem. So we can have collisions in objects that are undergoing rotational motion. Last class, we took a look at conservation of angular momentum, right? But we only considered it for a single object whose moment of inertia is changing throughout its motion. So let's think now about 2 different objects that are coming together to collide. So we've got, in this problem, we've got a puck on a table, and that puck is sliding towards a stick that is nailed down to the table on one end. The puck has some mass, and it has an initial velocity, an initial translational velocity, and it sticks to the end of the stick once it strikes it, once it undergoes that collision. And then they move together after that. They're moving together as one thing as they rotate around after that collision. So let's first, for the puck, find the angular velocity. So if we think about before the collision, it's going to have some velocity, right? And its velocity is 30 meters per second. And it's moving at some or a specific velocity towards the stick, right? And at any point, we can think about its radius away from that point of pivot that it will eventually pivot around once it starts spinning with the stick after the collision, right? But as we get closer and closer and going right to the collision, right before it begins to hit that, right before it hits that stick, it's going to be at some position away from that point of pivot. And that position is exactly the radius of that stick, right? Its distance away. So its radius is 1.20 meters away from that point of pivot where it meets that stick. And it still has that velocity of 30 meters per second. And so since we know those 2 things, at this instant right here before the collision, at this instant, we can find an angular velocity, right? And its angular velocity is going to be equal to its velocity divided by its distance away from that point of rotation. Now, it hasn't technically started rotating just yet, but right after it hits here, it is going to start rotating. So right at this instant, we can pretend it has some angular velocity, and that angular velocity would be equal to its velocity, its translational velocity, which is 30 meters per second, divided by its distance away from that point of pivot that it will then start rotating around, which is 1.2 meters. And those meters cancel out, and we end up with a radians per second. And if we take 30 divided by 1.2, we end up with 25 radians per second. All right. So again, it is not undergoing any angular velocity at this point in time, but we can determine its angular velocity relative to that pivot point if it were revolving at that speed of 30 meters per second, which it will start revolving right after that collision. All right, and now that we know the angular velocity of that disk right before the collision, then we can determine its angular momentum. And because we know that our angular momentum, or capital L, equals our moment of inertia for an object times its angular velocity, right? So let's quickly think about what our moment of inertia will look like, what moment of inertia equation we'll be working with for our disk, right? So we know that our axis of rotation is right here, right? And it is some distance away from the center of mass of the disk. Now, for the stick itself, right? the stick is rotating around that axis of rotation, and some portion of it is right next to that axis of rotation, and then some portion of it is further away, right? So we care about its distribution of mass around that axis of rotation. However, for the puck, all of its mass is away from its center of mass. All of it is away from that axis of rotation. So we can treat it just like a point, which means that its moment of inertia for the disk, we can call just its mass times its radius away from that axis of rotation squared. We don't need to worry about 1/2 or 2/3 or 2/5 or anything like that, because all of its mass is away from that axis of rotation. So its distribution of mass around that axis, it doesn't matter. All of its mass is away from that axis of rotation. So that means we can take our moment of inertia, we can just substitute in mr squared times our angular velocity, and we can get our angular momentum. And so if we take our mass, which was 50 kilograms, so that's 0.050 kilograms, sorry, 50 grams is 0.05 kilograms, times our radius, which again, it is striking 1.2 meters away from the axis of rotation. We're going to square that. And then times our angular velocity that we already found, 25 radians per second. You notice kilograms meters squared per second squared. And we should end up with 1.8, and again, kilograms meters squared per seconds. Sorry, not second squared, is what we end up with it. And that is those are our units for angular momentum of the disk directly before the collision. So collisions in rotational motion work the exact same way, or very similarly to collisions in translational motion. Meaning that if we take our angular momentum for our first object, in this case the disk, and we add to that our initial angular momentum for the second object, in this case I'll call it the stick, that's going to equal our final angular momentum for the disk plus the final angular momentum of our stick. Right. And we can break these up into, since our angular momentum is our moment of inertia times our initial angular velocity for the disk, will be, if we add that to our moment of inertia for the stick times our initial angular velocity for the stick, that's going to equal our final or moment of inertia for the stick times its, for the disk times its final angular velocity plus the moment of inertia for the stick times its final angular velocity, right? And since we know that those two things are moving together, it's an inelastic collision afterwards, we can just take and we can add our moment of inertia for the disk plus the moment of inertia for the stick, and that will be multiplied times the angular momentum that they both have together at the end, since they're moving together. And one more thing to simplify things a little bit here, right, is that we know that initially our stick has an angular velocity of 0. So that means that this term goes away. So our moment of inertia for the disk times its initial angular velocity equals the 2 moments of inertia added together times the final angular velocity of our system, right? And the good news is we already have a term for this, right? We know that that is equal to 1.8 kilogram meter squared per second. And so if we take and divide that by our 2 moments of inertia added together, do it on one side, we have to do that on the other side, then we'll end up with our final angular momentum will equal our moment of inertia, our angular momentum for the disk divided by our moment of inertia for the disk plus our moment of inertia for the stick. Okay, so I'm just going to move this equation up here so we get a little bit of room to work. And again, we already know our angular momentum for the disk prior to the collision. So let's think about what our moment of inertias are. We already found a moment of inertia for the disk, right? We said that it's the mass of the disk times that radius or the length of the stick squared. And for a moment of inertia for the stick, we can go and we can look up an equation for a rod that is revolving or rotating around one of its ends. And if we did, we would get that it is 1/3 of its mass, in this case the mass of the stick, times its length, or we're just going to call that our radius here, squared. So we can plug those terms
into our equation over here. So we got our initial angular momentum for the disk, which again, we already found in part B, divided by the mass of the disk times the radius of the stick squared, or the diameter of the stick, really, the length of the stick squared, plus 1/3 times the mass of the stick times radius squared. So we just got to plug our numbers in over here. So we already had a number up on top for 1.8 kilogram meters squared per second is our initial angular momentum of the disk. And then we've got our mass of the disk is 0.5 kilograms times the length of the rod, which is 1.2 meters. And then we're going to square that. And then plus 1/3 times the mass of the 1/3 times the mass of the stick, which is 2 kilograms, and then times the length of the stick, which is 1.2 meters squared. Great. And then if we plug that all in, we should end up with 1.74. And we got kilograms meters squared plus kilogram meters squared. So those kilogram meters squared are going to cancel out with what's on top. And we'll end up with just seconds on the denominator, or if we wanted to, call that radians per second.
Okay, so now with what we figured out so far, we can find our total kinetic energy both before and after the collision, right? And hopefully there'll be some difference there, because unless we have an elastic collision, then we're going to lose some energy during this collision, right? So let's think about our initial kinetic energy. So that's going to be our kinetic energy, our initial kinetic energy of the disk, plus our initial kinetic energy of the rod or the stick, right? And we know that since the stick wasn't initially moving, then this kinetic energy is going to be 0, right? So really the only kinetic energy we have in the beginning is our kinetic energy of the disk, which is 1/2 times the mass of the disk times the velocity of the disk, the initial velocity of the disk squared, right? So we'll take 1/2 times 0.05 kilograms times its initial its initial translational velocity was 30 meters per second, and we can square that. So we can get its translational kinetic energy, because at this point it didn't have any rotational kinetic energy, right? And so if we take 30 squared, it'd be 900. Half of that would be 450. Another half of that would be 225, and then a tenth of that would be 22.5. So this should be 22.5 joules will be our initial kinetic energy. And we can take our final kinetic energy, right? And our final kinetic energy is going to equal our kinetic energy of the disk plus our kinetic energy of the stick again. In this case, both the final kinetic energies. And they both do have some energy at the end, right? They're both moving. They're both undergoing some angular velocity, some omega. Right. So that means that now we can take and we can get their rotational kinetic energies. So we'll take the moment of inertia of the disk around that axis of rotation times its angular velocity. That's the final angular velocity squared, which we already found. And we can add that to 1/2 times the moment of inertia of the stick times that final angular velocity squared. Right. And then we can break those down a little bit further, because we know that the moment of inertia of the disk around that axis of rotation, right, is the mass of the disk times the radius of the stick squared. And our moment of inertia for the stick now, we know that a rod that's rotating around one end, if we look that up, is 1/3 times its mass times, again, the length of that stick, which we're calling the radius squared. So we plug those all in, right? So we get 1/2 times our moment of inertia for the disk, which is mdr squared. And that's times our final angular velocity squared. And then plus 1/2 times our moment of inertia for the stick, which is 1/3 ms r squared. And then times our final angular velocity squared. Right, and then if we wanted to pull out all of the numbers there, we can simplify a little bit. So we got 1/2 md empty r squared angular velocity squared plus 1/6 mass of the stick radius squared times final angular velocity squared. So this should be final angular velocity. And so if we want to pull everything out there, we really have 1/2 times the mass of the disk plus 1/6 times the mass of the stick. And then times both of them are being multiplied by r squared and angular velocity squared, right? So let me erase some things. Okay, so and then if we clean that up a little bit, we've got our expression we just found out, right? So we can plug in some numbers for those. That's 1/2 times 0.05 kilograms plus 1/6 times the mass of the stick, which is 2 kilograms, and then all that's multiplied by 1.2 meters, and we're squaring that, and times our angular velocity that we already found is 1.74 radians per second, and that is also squared. And in the end, we get kilograms from this term, from this first term, right? Kilograms, we get meters squared, and we get over second squared, which, as we know, is in joules. And so if you run the numbers on that, we should get 1.57, give or take a rounding error, joules for our final kinetic energy of the system. And we see there's a difference between our initial kinetic energy and our final kinetic energy. And again, that would be due to we are experiencing an inelastic collision, a totally inelastic collision, right? So this should be the maximum amount of kinetic energy we can lose in a collision, because after they collided, they ended up sticking together, right? Okay, so we compared our kinetic energy before and after the collision. Let's now take and compare our momentum before and after the collision. So we already took a look at our rotational or our angular momentum. Let's think about our linear momentum. So if we think about our linear momentum before the collision, we've got our linear momentum of the disk plus our linear momentum of the stick. Right, and again, the linear momentum of the stick should be 0 because it has 0 angular velocity and 0 translational velocity, right? So that should be 0. So we're really just looking at the momentum of the disk, which is the mass of the disk times the velocity of the disk, right? And we know all those things is 0.05 kilograms times 30 meters per second. And so if we run the numbers on that, half of 30 is 15, and then times 0.1, that gets us 1.5 kilograms meters per second is our total linear momentum for the system before the collision. All right, now let's think about our total linear momentum after the collision. So our P prime, or our final total momentum, will have to equal our final momentum for the disk plus our final momentum for the stick, right? And so if we want our linear momentum, right, our linear momentum equals mass times velocity times our translational or our linear velocity, right? So we know our final angular velocity, right? And we know there's a relationship between angular velocity, and that is you take your your translational velocity, because we know there's a relationship between our angular velocity and our translational velocity. And if we divide that translational velocity by r, then we get our angular velocity, right? And conversely, if we have if we want our velocity and we have our angular velocity, we can multiply that times r. All right, so that's easy enough for the disk, right? That means that for the disk, we can take the mass of the disk times the final angular velocity, times the final angular velocity. And then if we multiply it times r, then we get our final velocity for the disk, right? But we also need to figure that out for the stick, because again, we can take our mass of the stick, but then we want to multiply it times the final velocity for the stick. And this is a little bit trickier to think about. So let's just think about what's going on with this stick as it rotates over here. So I'm going to redraw that over here. So the disk comes and hits the stick, right? And the stick starts having some angular velocity, which we know is 1.74 radians per second, right? So let's think about what does that mean for its translational velocity. And of course, our velocity, we already talked about, equals our angular velocity times our radius, right? But for translational velocity, we're worried about the velocity of our center of mass, right? So what is happening with the center of mass as we rotate around that pivot point on the end of the stick, right? Where is the center of mass in this stick? It's really the center of mass is right here. And so it is a distance of 1/2 of its length, which we're calling radius. So 1/2 of the radius away from that pivot point, right? So its distance is only 1/2 of radius. And so if we think about the radius we want to plug in here, it's really 1/2 of the radius. So our velocity for the center of mass of the stick equals the angular velocity, right? Because the whole thing is displacing with that angular velocity, whether you look down at the bottom or at the top or right in the middle. All of it is moving some number of radians per second, and it will all move together to go back to the same position after one full revolution of 2 pi, right, over some amount of time. So our angular velocity is consistent across all pieces of the stick, and yet if we look at any position, any point on the stick, right? At any point on the stick, some points will have a higher velocity than others, right? Right here, we're going to have the maximum velocity, translational velocity. But if we look at a point right here, it's not really moving all that fast because it's not displacing all that much distance, even though it's going through the same angular velocity. So we're looking for the center of mass's velocity here. And our center of mass, again, is 1/2 of the radius. So we'll still take our angular velocity because all of the stick is moving with that same angular velocity, but then we'll multiply it times, in this case, the center of mass is only 1/2 radius away from that axis of rotation. So if we plug that in up into our original equation, we got, again, md times our angular velocity prime times radius plus the mass of the stick times, instead of that final linear velocity, we're looking for the final linear velocity of the center of mass. That's going to be our angular velocity, our final angular velocity times 1/2 of the radius. All right, so if I rewrite this over here, just to give us a little bit more room to work, then we can plug in our numbers as usual. 0.05 kilograms, the mass of the disk, times our angular velocity is 1.74 radians per second. And that's times our radius, which is 1.2 meters. And then we can add to that 1/2 of the mass of the stick, which is 2 kilograms, times our angular velocity, 1.74 radians per second, times our radius, 1.2 meters. When we plug all those into the calculator, we should end up with a final momentum that should be about 2.2 kilogram meters per second is our final translational momentum of this system. All right, so now what's interesting here is that we're familiar with losing kinetic energy throughout a collision, right? Because when we have an inelastic collision, we end up losing kinetic energy by those two objects sticking together. Or in most real-world collisions, we lose energy anyway because we're going to have some amount of work lost to non-conservative forces like heat or sound or something like that, right? So what is a little bit different, however, from when we were thinking about collisions in translational motion is that we generally had in the beginning the same momentum as we finish with, right? So that's, the momentum we end with is the same momentum we had in the beginning because there's that conservation of linear momentum, right? In this case, we don't see that. And so let's think about why that is. And the answer is that if we consider from the rod's perspective, the stick's perspective, right? It gets hit by the disc. So it feels some force at one end. And if we imagine it on a frictionless table, what would happen to that stick if it got bopped on one end? Well, what would happen if it wasn't nailed down anywhere is it would rotate around its center of mass, right, is where its angular momentum would be in the absence of friction or any other forces. And so really, if we look on this end, it experiences a force, right? And this end is going to experience some angular velocity, right? However, we don't have a situation like that. Instead, we have it nailed down on one end, right? So really what happens is it experiences the force on one end of that disk hitting it, right? And the other end, on the opposite side of the center of mass, wants to push in. And so on this nail, it's exerting some amount of force is being applied on the nail. And the nail itself is, by Newton's third law, pushing back with some reaction force. Right? I'll call that FR, some reaction force. And that reaction force is pushing the stick, right? And so there is an external force here. There is a net external force to our system, and that next net external force was responsible for a gain in momentum as we look from the beginning of this collision to the end of the collision. So our momentum is not conserved because we actually do have an external force here. We have an external force being applied by that nail as it resists that angular motion of the stick around its center of mass. Instead, redirects it around its pivot, its position, which is the pivot point for this system. So that's why we end up with a change in momentum that is actually a gain in momentum because we've got an external force pushing us in the direction of our momentum of the system. All right, let's think about one final thing here before we transition to discussing the rest of this in class, and that is the direction of angular velocity and momentum and torque. Because so far, we've talked about our direction for things that are rotating in terms of clockwise or counterclockwise, right? So there's some other things we can think about, right? We can think about right, left, clockwise, counterclockwise. And if we look at something like this disk down here spinning, right? If we look at one point on our disk over here, this, since it is, and we look at our disk down here spinning, then we've got an angular velocity right around this direction. If we look at one point on the far end of that disk, that point will be moving in the left direction. However, if we look at a point on the close end of the disk, that point will be moving to the right, right? So right and left obviously aren't super useful for us. What we have done so far is we've also thought in terms of clockwise and counterclockwise, right? And if we look down on the disk from above, right, then what we see is it is moving with a counterclockwise rotation, right? So maybe that's a useful perspective and direction for this angular velocity, right? And by extension, our angular momentum. However, if we look up from below, then we see it again spinning like this, but now our perspective from the bottom will be that it is moving in a clockwise direction. So that means that our right and our left aren't terribly useful. Actually, our clockwise and counterclockwise aren't super useful because it depends on which side of the spinning system we're looking at. So the issue here is that all of these are kind of useless to us because they're all relative to our perspective. So they're not good absolute descriptions of the direction of our angular velocity, our momentum, or our torque. All of which, as we know, are vectors. And so they do have both magnitude and direction. So our direction is important here. So since direction is important, we came up with a convention to describe our direction. And the way that we describe this direction is that rather than thinking in the plane of the disk itself, we think in terms of an axis or a orthogonal or normal or perpendicular axis of coming out of that plane of rotation. All right. So obviously this disk is rotating in the, if we want to call this the X and the Y direction, X and Y, X and Y. And then coming out of that would be a Z direction. So it's on the z-axis that we describe our angular, any of these rotational vectors. And what we use is this thing called the right-hand rule. And the right-hand rule says basically if you take your fingers and you curl them around in the direction of that motion, be it the torque or the angular velocity or the angular momentum, then your thumb of your right hand will be pointing up in what we call the positive direction. So this defines the positive direction for that vector. Okay, so this equals the right hand rule gives us our positive direction, and then the opposite direction, obviously, this would be our positive, and this would be the negative direction of our motion. So, what exactly does that mean in practice, and how can we use that? We're going to discuss that in class, and we're going to discuss that using a gyroscope, right? But just a quick word on where this comes from, which is why do we use our right hand but not our left hand? And the answer is simply it's just a convention. So at some point it was decided we'll use the right hand. Usually we favor right-handed. 90% of the population is right-handed, so I guess generally that gets favored. So at some point we locked this in that our convention is that we use the right hand rather than the left hand, and the right hand gives us our positive direction. However, if you wanted to use your left hand to curl your fingers, you would curl them in the opposite direction, and then your thumb actually would point it down, and that would be your negative direction for this for this for this example. And I drew this wrong. You'd curl your fingers in that direction, and then your thumb would be pointed down, and that would give you your negative direction. All right. So your right hand gives you your positive. Your left hand gives you your negative. So all that really matters is you're consistent with which hand you're using, because all of these, as you probably know, positive and negative, all of the time are defined by convention. Why do we usually use up as positive? Well, we don't have to. It doesn't really matter. But what does matter is that we define one direction as positive, and then everything else in relation to that direction, right? So if we're going to use our right hand rule, we just need to be consistent with that. If you want to use your left hand, you could. All of your positives and negatives will just be the opposite of what everyone else is calculating, but you'll get the exact same numbers, give or take a negative sign. All right. So what we're going to do is we're going to take a look at this in class, and we're going to use an example of a gyroscope in order to figure out what's going on. All right. So gyroscope looks kind of like this, and it will kind of maintain a stable position as it rotates against what seems to be against the odds of gravity and other forces that are acting on it. So we will explore this in class when we talk about this lesson. All right. Thank you for learning today, and I will see you in class.